All right, 12 o'clock, noon. Good afternoon. Let's get started. I see there's already a discussion on the chat. So how you folks are doing? It's TGIF again, Friday. Oh, thank you. I'm doing quite all right. And I can see there's discussion about the test. So what do you think about the test? Too long? Time crunch? Fair? Too long? Not hard, but very long? Too long? Okay, too many. Okay, I'm getting. So why don't we run their submini poll? Well, they officially call them submini polls for the hardest question on test 4. Okay, and that should hopefully give us some information to think about what we can do. Okay, so can you see the poll? Well, you can treat hardest as most time consuming, you know. Yeah, and yeah, someone is saying the recursion in MIPS can be a headache. So Q2 was, question 2 was not that easy as well. And I actually looked at some random submissions, and I think overall, just based on the small sample of submissions that I looked at, they were very decent. They were on average much better than the previous test, S3. So yeah, please answer this poll. However you want to define the hardest, and then we can think what we can do about it. Okay, and discuss it next time when we have all the poll results. Okay, so and actually, if you're interested, out of the submissions that I looked at, I don't think I've seen many. I'm trying to think if I've seen at least one that would have question 6 correct. So, if you asked me, based on what I've seen in submissions, I would say probably question 6 was not that easy. Turned out to be not that easy. Yeah, and Q1 had to be kind of on the long side, because we wanted to see how you handle the chain of calls, so that we have at least 3 procedures for that. Okay, so one procedure calls the other, and that other calls the third. So, well, someone says they didn't practice anything like U6, but there was a very conceptually similar question on the practice in the practice set, where you had to do like a 4 decoder using 2 decoders, something like that. Okay, so our panelists ready? Okay, are you folks here? Okay, all right, cool. So let's get started with our agenda. Let me start sharing something before you get too bored. But I looked actually at the grades. So I updated Rainbow grades this morning, and because homework 3 was graded, and all grades were posted for homework 3. And I wanted to look at the results, and actually we have like slightly over 30% of the class currently above A-. Okay, so I think it's a pretty good result. And we have as usual, unfortunately, a certain number of people, a handful of people who are below D. Um, and so I just wanted to give, and there's not that many. I think it's about like 10 people or so. So in a class of 220 people, I think it's not that a significant number, but still, some of those people are close to the D threshold. Some of those people are way, way, way behind. So just wanted to remind you that we have today, the 22nd is the drop deadline. So if for some reason you stopped attending the class, if you're no longer engaged with the class, and you're planning on dropping it, today is the deadline. Okay, so dropping after the drop deadline is possible, but it's a headache because you have to do like all the paperwork and justification, and it may actually not be approved. So if you were to drop this class, please do it today. Okay, and all right. Yeah, we will discuss the solutions for the test when they're graded. Okay, so when because some people who had excused absences are still to take the test. Their test will be different, but still, just discussing anything related to the contents of the exam might help them. All right, because topics are the same, so I don't really want to get into too much detail about the contents of the test as to not give those people who have official excuses and are about to take makeup any kind of unfair advantage over the rest of you. We should move homework 4 to Thursday since we all have a midterm and we have had them on Thursday the past few weeks. Okay, so that can be done actually, unless eventually we will have to go back to Tuesday homework assignments in our schedule, right? Because otherwise, there is no way we would be able to grade the last assignment on time. So at least the last assignment needs to be on Tuesday. So whether we go back to Tuesday homework schedule on this homework or on the next homework is up to you. If yeah, sure. I mean, if a sufficient number of people ask to move the deadline, and if there is no one who would, or very few people who say no, we should not do that, we can totally do that. Okay, so let me ask then this. I already see that many people are asking to move the deadline for the homework from Tuesday to Thursday. So if there is anyone who objects, and you can just send me a private DM in the chat. If you have any problems with this potential decision, if if you see that how it would, I don't know why, but maybe you see how it would disadvantage you, then please let me know. Okay, in the next couple of minutes. Okay. Because I think it's a pretty easy decision, but I want to make sure that we do not discount anyone who might have a problem with this. The last homework will be due the last week of classes. And since the last day of classes is Friday, if that homework is due on Thursday, and then people can use 2 late days, up to 2 late days on top of that, which means we cannot start grading until Sunday. And remember, there will be also an exam that week, so it will just completely overload and overwhelm our TAs and mentors. And we have to get the grades early, the following week, like the final grades for the exam. So that's why we will have to make at least the final, the last homework due on Tuesday, the last week of classes. Okay, all right. So yeah, and we would be going over the floating point numbers. Okay, so but I see the concern, and then let's do exactly this. Let's move the homework due date to all right Tuesday, Wednesday, Thursday, right? It's going to be the 28th. Okay? We good? All right, cool. So moving on. All right, I mentioned homework 3, grades posted. Homework 4, we just discussed. Exam 4 being graded. And then slides, we need to finish the ALU stuff and then talk about the remaining topics in this chapter 3 slash appendix B. Okay, without further ado. Oh, and yeah, actually, before we get started, let's do something that hopefully explains what I'm expecting on that same homework that we just moved the deadline to Thursday, and that would be how you test your circuits. Okay, so let me come up with some circuit. And I don't really care what function it implements. It can be, I don't know, anything. And then I want to do this, for example. So whatever function you have, and you have inputs, and I need to have an output, right? So, and you need to test this circuit, okay? And of course, one way to test it, and you know that's what I mean when I say, you know, please test it for all combinations of. Yeah, this is just, you know, a few gates, and well, yeah, I was just kind of doing it at random. Yeah, but it's a few gates. Okay, whatever. It's an OR gate. All right, I agree. So um, where I'm going with this is, well, one way to test it is to go through all combinations of inputs, and first make sure that yeah. So let's make one of them inverted. Or maybe two of them inverted. I don't know. Whatever. All right. So first, make sure you label everything. Okay. So like if your variables in the formula are A and B, then of course those are your inputs. And we should label them. And of course the function should have its name. You can come up with whatever name you like if it's not given, but like, you know, on the exam, for example, it was given the name. I think it was D, or it can be F, whatever. But make sure that you label them. It's 30% of the class are above A minus. Yep. Okay. So once we've labeled everything, we drew this diagram, and then we want to test it. So you have to go through all combinations of inputs. There are 4 in this case, right? A is 1, B is 0, B is 1, A is 0. Okay, and A1 and B1 are both, yeah. So now I looks like I got a constant 1. Okay, so let me get rid of. It's not really that important. So okay, well, whatever. Go back to my original design. Okay. All right, whatever. So you test all combinations of inputs, and you make a screenshot, and you show that, all right, when A is 1, B is 0, the function is 1. When A is 0, B is 0, the function is 0. Okay, and that's how you test your circuit. Okay, and you have to show us the result, right? If you're saying that, oh, this circuit implements this Boolean function, and then you have a truth table for that Boolean function, then you have to show us that this circuit indeed implements this Boolean function as well. And of course, you know, it gets a little tedious with 2 inputs. Of course, it's going to get even more tedious with more inputs, like if you have to manually, you know, manually switch between them. Yes, for we need a screenshot for each combination if the number of combinations is not huge. Of course, if we're not going to be asking you to do 128 combinations, 128 screenshots. That would be too much. That's why I think in one of their problems on the homework we say, well, just do your best to show us that that your circuit is correct, that it works correctly, but we do not expect you to do exhaustive testing. Exhaustive would mean like all combinations. Okay, and for the K map, are we allowed to put in a screenshot of a picture of the map, or do we have to make it in docs overleaf, whatever? So you yeah, so someone suggests just take a snip of the screen and save it into file. Yeah, I think that would be best. Or someone suggests exactly what I was going to say. That there is a latex package for pretty much anything, including K maps. So if you're using latex, I think you're good. Yeah. If you're using Word or something else, you can also do a K map in using Excel and then insert that. So I would still ask people to use some kind of tool to draw their K maps because handwriting is very often hard to read. On the exam, it's inevitable. We live. We hopefully our TAs handle that well. But on the homework, you have more time, so it would probably be nice to just use some kind of tool so that your result looks pretty and not just a picture taken from a camera from some piece of paper, and a very faint drawing with a pencil that we can barely read, in bad lighting, right? So do something a little nicer if you can, please. All right, so what I was going with this, I'm back to my circuit. Okay, so instead of, or in addition to doing that, however you want to do it, you can actually sort of automate your testing. And the way you can do it is by using a clock. So in a clock, okay, we have. So what is a clock? It's basically the thing that oscillates between 0 and 1 with a certain frequency. Okay, so when we were previously talking about performance analysis and their clock frequency of a processor, right? So their waveform, the shape of the signal looks exactly like shown on this clock component. And what you can do is actually use it. So if you click on here, there's a clock delay. Okay, and if you combine several clocks, you can achieve a very interesting result that can save you time with testing. So let me bring up my whiteboard. Okay, and here we are. All right, so and I start with just a clock. Right, so suppose this is the clock that you feed to input A, right? So this is 0 level or false, this is 1 level or true. It doesn't matter, it's all just a convention. You can flip them, nothing really changes. But one, if we are using open circuits, then one would correspond to their to their true value. Okay, and now what we want to do is we have two variables, A and B, and let's put them in this order. All right, so I want to test all 4 combinations. Okay, and I can see that, well, wow, my A is 0 to 1, 1 to 0, 0 to 1, and then if we continue, all right, it's going to be 1 to 0. So yeah, it kind of looks exactly what I can do with the clock, right? So my A just goes from 0 to 1, from 1 to 0, and so forth. And now I just need to come up with the waveform for B. So can someone tell me what the waveform for B I should choose for my clock, or how different it's going to be from the waveform of A? To make the period longer. Exactly. Like if you look at this, right, here's B at 0, and then it switches to being B at 1. And so if you think about it, it's exactly twice the period of A. This is what I want. So if we had B here at 0, okay, and the period, just remember, so let's say this is, yeah, and let's start with 0, okay? So, and now, okay, so this is 1, this is 0, this is 1, okay, and we want B to be at 0, Y, A is 0 and 1, so erase like that. So it's going to be, all right, so this is 0, and then B goes to 1 and stays at 1 at least until this time. All right, so it's 0 and 1, and then it goes down, and then and so forth. Okay, so we see that, well, it's not exactly, you know, what I want. Well, it's actually is, right. So if t0 is here, right, so this is our time 0, okay, then we see that B0 stays low, stays at 0 for like 2 half periods, and then it stays at 1 for 2 half periods of A. So the period of B is twice as long. Okay, and if we look at each half period of A, we can see, all right, so here, right, in this period, we have B at 0, A at 0. In this period, we have B at 0, A at 1. In this period, we have B at 1, A at 0. In this period, we have both A and B at 1. So if you set up these two clocks, then, and of course, the clocks would just, you know, keep running, but you see that you are basically checking their all possible combinations if you set up your clocks like that, right? So if you feed those clocks to your inputs, then the output will go through their, you know, in a cycle, it will go through all 4 states that we want to check, and then through those 4 states again, and so forth. Okay, so that's exactly what we can do in open circuits. So let's go back, and now we just need to make sure that our clock delay, I believe that's how this open circuits component calls their period. So clock delay, we make it twice as long, and you can see that it kind of changes the color slower. Okay, and so we can then just connect. Yeah, it's not letting me do that, so you cannot have 2 inputs connected together. So I'm going to do something like that, or a better way, actually. Let me back up. Right, a better way would be to have a buffer, right, which is a buffer. It doesn't change the signal, but it allows me to kind of do this and then connect this one thing to the buffer, and then with my second input, let me connect the buffer first. Okay, to here. All right, yeah, it's not letting me do that, of course, but all right, not a big deal. I here and here. All right, and now you can see how values change, and that only when we have two zeros, the output is 0. The LED is not lit, so it is indeed an OR gate. Okay, just not the minimal, not the optimal. But you can see by the color. So when the color is blue, it is 1. When the color is white, it is 0. We can see that the circuit kind of checks itself. Yeah, and the buffer allows us to then, so if I'm not happy with this, now that I have a buffer, right, I can disconnect my, my clock and connect some other components so that the rest of the circuitry is not, like, I do not lose the other of, the other wires. So, I can do, I can do a button or something like that. All right, so I just wanted to show you this approach with using the clock. So yeah, for the homework, it's just the organizational thing, and how you can make it actually easier. And we will see that, one thing that is lacking in open circuits, and I talked to their devs, and they have it in, in some distant plans, they have an idea of implementing this, but it would be nice to actually watch the waveform. Okay, and we will look, I don't know, today or next time at another tool that actually allows you to look at the waveform, right? To visualize the waveform, and I think that would be very convenient. But for homework 4, it's sufficient if you just do this in open circuits, and you don't need to use any other tools, right? Just set up your clocks correctly, and then yeah, unfortunately in open circuits you cannot control the speed of the simulation, but one thing you can control is their clock delays. So if we change this to 5 and we change this, so it's if it's too fast for you and you're not really, understanding where your circuit is, you can just increase the periods of the clocks. All right, so now it's 1 and 1 and the output is 1. Now it is 0 and 0 and the output is 0. Next we're going to have 0 and 1 and the output is 1. So just you can make it slower this way, right, with clocks. Okay. All right, so let's get back to our slides. And so we were going to talk about ALU and constructing the ALU, or arithmetic and logical unit. Some people say ALU, some people say ALU, doesn't really matter. So their basic, their most important job of a computer is to compute, which means to perform arithmetic operations, right? That's what we usually say when we say computers compute, right? Not to play video games, although, of course, behind all the video games, there's just, massive amounts of computations. But, that's where everything started. Computers compute. Computers can do, can perform arithmetic operations like addition, subtraction, multiplication, and so forth, right? So they're one of the key components inside a processor is an ALU, arithmetic and logic unit, that performs those arithmetic operations, and on top of that, logic operations. What are logic operations? They are Boolean operations like and, or, X, or everything that we've discussed. So we want this single unit to perform those operations. And of course, we will need to tell that unit which operation we want at any given moment of time. So we are getting to a very important concept of a control signal. Okay, we have a single black box that can do multiple things, and we need to control it by telling it which specific operation we want at any given moment of time. So let's start with an ALU, with designing an ALU that can perform addition, subtraction, and just two logic operations, and an OR. So for MIPS, we're going to need eventually a 32-bit ALU so that we can add 32-bit numbers. But we start very slow. Remember, we had it in one of the sub-mini polls. We had this idea, this question, which actually I don't know if any of you had a chance to look it up or Google it, right? About eating the elephant. So it is a well-known internet meme. Like, how do you eat an elephant? And the answer is you eat it, piece by piece, or one bite at a time. And here, I thought it's funny, right? So bite as in a little piece off, and bite as bit as a little piece off, and bit as 1/8 of a bite, right? So there's a play of words. I think it's pretty funny. So, and I thought that approach was very helpful if you adopted it for the previous homework when you had this huge matrix multiplication thing. Just do it, little by little. Make the problem simpler, solve a simpler problem, and then add complexity once you've done the simpler problem and debugged and verified that it worked. And it's the same idea here with designing a 32-bit ALU, right? Instead of designing a 32-bit component right off the bat, let's do a 1-bit and then see if we can somehow combine 1-bit pieces to build a 32-bit component. And it was the same idea that we've seen also earlier with, like, oh, we have a 2 decoder. How do we, can we use these 2 decoders to build a 4 decoder, or can we use 2 input multiplexers to build a 4 input multiplexer? All right, so starting small, designing a 1-bit ALU, and we just then take a bunch of them, and hopefully we can see how we can, grab a bunch of single-bit ALUs to make a 32-bit ALU. Okay, it might be very trivial for some operations, and very non-trivial, very tricky for others. So if you think about their bitwise operations, like our logic operations, and or then they are done independently on different bits. So it would be very easy to build a 32-bit unit that can do an or an and out of units that can do 1-bit or and and. Okay, or well, on 2 1-bit values. Okay, so because bits are independent. If you think about things like addition, then bits are no longer independent because we can have carry. Okay, and in case of subtraction, we can have borrow. So we cannot just compute each bit independently, and that's why combining smaller bit components into larger bit components for those operations might be a little more complicated. But overall, we take the bottom up approach. We build small units and then just combine them, a bunch of them, and wire them properly to build larger components, larger units. All right, so first we want to design a single box, okay, a component that can compute either and or. So start small, forget about addition and subtraction for now, just and or. And there are 2 operations that we want our component to perform. Therefore, we need a control input to determine which operation is performed. And since there are only 2 operations, we only need 1 wire, 1 bit of the control signal. And we call it OP, operation. And we pretty much arbitrarily decide how to encode operations with bit values. Okay, so for example, we can say if OP is 0, then our simple ALU needs to perform an AND. If OP is 1, then it has to do an OR. Okay, you could have swapped it and do 1 is AND, 0 is OR. It doesn't matter, but you have to make up your mind, and then you have to stick to this convention because it's going to be implemented in hardware. So it's going to be hard-coded which code corresponds to which operation. Okay, so we just decided 0 is AND, 1 in OR, and we just draw our box. We have 3 bits of input, right? A, B. Again, remember, A and B are 1-bit values. OP is another 1-bit value. It's a control signal, and the result is the result. And then we build this truth table. So truth table just describes the result that we want to achieve. And as we previously decided, when OP is 0, this is an AND. And therefore, the result is actually the result for an AND, where the result is 1 only when both A and B are 1. And then OP of 1 is an OR, and then obviously, this part of the truth table corresponds to the truth table of an OR. Okay, so, and we can express it with the formula, of course, right? The result is A times B when OP is 0. Result is A plus B when OP is 1, where times corresponds to and plus corresponds to an OR. And once we've done this, well, from this point, you already should know what to do and how to take it further, right? We have a truth table. It's you can just forget about what those bits mean and just do your SOP or POS or your K-map or any of the methods that allow you to synthesize a circuit based on the truth table. And when you synthesize synthesize the circuit, then you will determine what is inside this black box that we just started with a black box. All right, so that's exactly what I said. SOP, POS, to determine the circuitry that will implement this ALU, and we could also adopt a slightly more intelligent approach rather than just mechanically, doing SOP, POS, or K-map from the truth table. We could look at the semantics of the operations, and we could look at at what this actually does. So we have an OR gate and an AND gate that can perform the functions that do what we want. And then we just need to have some component that will decide which of the results is routed to the result. Does the result get the value of the output of an AND gate, or does the result get the output of an OR gate? And hopefully you remember what that component is. Well, it's written on the slide anyway, right? So we could use a 2-input multiplexer to pick which result to route to the ultimate output of our circuit, our 1-bit ALU, the simple ALU with just 2 logic operations and an OR. So we could, we could have implemented this 1-bit and OR ALU with just AND and OR and NOT gates by doing POS or SOP, or we could have done this, right? And now, it's quite obvious here, hopefully, that when OP is 0, it means that this is routed. So the result is really A and B. Okay, and if OP is 1, then it is routed like that. And the result, well, it's not 0. It's output or the result. Oh, no, hold on. It's the value of the control signal. So let me erase it. So this is 0. This is correct, right? So because this is the value of the OP signal, right? And when OP is 1, the result is A plus B. Okay, so you could do that as well, and that's pretty much it. Right. So with addition, it gets a little trickier. So let me actually switch to my notes from a few lectures ago when we were discussing 2's complement and just in general how numbers are encoded in in binary systems. And of course, our computers are currently all binary systems. So let's discard this and let's go to our notes from the lecture. So remember those notes that we went over. But one thing was interesting here. Imagine we are doing a binary addition of 2 numbers. Okay, and then we were discussing here in that context, like their 2's complement notation, their sign magnitude notation, and all that stuff. Okay, so but we kind of left behind their question, like, well, how do you actually do binary addition? Here we were doing it just manually, like using the grade school algorithm that we learned for the decimal system, and we discussed that it applies, completely. It's completely true. It applies to any other number system, be that binary or hexadecimal. But we were doing this manually here. So what would be actually the way to add two numbers in real, in real computers? All right. So we know there is an or, we know there is an and. We talked about them. We know there is an not. Okay, and so here are the truth table. Okay, but if we decide to do addition, okay, which of those operations would work? Okay, and if we try or, okay, and this is our notation for or in Boolean algebra, a plus b. But we have to see here that a plus b is really an or, it's not an addition. Why? Well, because 0 and 0 is 0, 0 and 1 is 1, 1 and 0 is 1. But if we add 1 and 1, we should have 0, and 1 would be their carry to the next bit. So this line clearly shows that, well, or cannot be used for addition. Okay, it's close. It gets 3 out of 4 rows correctly, but the fourth row is incorrect, right? Yeah, exactly. So we need to come up with something else. And here's the example that shows, yeah, compare with a Boolean single bit adder. If we choose plus or as the adder, it's not working correctly. Right? So we know that the result of addition should be 0 here, okay? And or would give us 0, okay? And the result of adding 1 and 1 would be 0, and there is a carry, of course, right? But, either way, we have to come up with something else, right? Or is not the right choice for addition. And then we can just try some other Boolean operation that we talked about before, and someone already guessed it correctly. It's XOR. Okay, so XOR would give us exactly the value for that bit that we want. It's not going to give us carry, right? If we just XOR A and B, we get the correct value for that result bit, but it's not going to give us carry. So for the carry, we have to we have to build some additional circuitry, but it should be easy. So how do I generate a carry signal? When is there going to be a carry from this bit? Exactly, it's an AND, because you see the only time we have a carry is when both A and B are ones, and that means that, oh, our carry signal is just A and B. So to implement addition, we need basically two gates, an XOR gate to compute the value of that bit, and an AND gate to compute the value of the carry into their next bit. Okay, and that's really the basis of building the adder. It's not going to be a full adder, because if we have a carry out, right, a carry from this bit to the next bit, to the next bit on the left, to the next more significant bit, then of course we need to build a circuit that would be able to also accept carry, or have an input signal called carry in. And so far in our discussion, this hasn't come up. So that would be the difference between a half adder and a full adder. A half adder would not have a carry in signal. It would only have the result and carry out signals. And then if we update it to a full adder, then it would also have a carry in signal. All right, so let's continue with our slides. So hopefully I convinced you that we can build a real 1-bit adder that performs addition, and we just need an XOR and an AND. But let's approach this also from this perspective of just building the truth table first, and we see that if we look at the result, right, and O0 here is their carry out, right? It's so A, B, and carry out into the next bit. We call it C out. Okay, so O naught, O sub 0 is only 1 when A and B are ones, and then O1 is the value of that bit is the sum of A and B without regard to carry out. And of course, it's only 1 when either A or B are 1, but not both at the same. Not both at the same time, right? And so we can just do our again one of the methods that we learned before to build this circuitry, right? So that is one way to do it, or we could do their XOR and AND as we discussed before, right? So here, if we are only limited to AND or and not gates, that would be how we do it, or we could do this. And now, so binary addition with our adder. So we have a 1-bit adder, but what we really want is something that can be used to implement the binary addition algorithm on real, values that are more than 1 bit long. So let's see how that, what else we need to do for that, right? So, and let's just do, and we've done this before, but let's follow this example. So 1 and 1 is 0. So 1 and 1 is really this, right? As we know, right? Because it is, 1 and 1 is 2 in decimal system. In binary system, we express 2 as 1, 0. Okay, so basically it means that in this bit it is 0, and then there is a carry into their carry out of 1 into their next bit. And then when we are summing for the next bit, we are summing everything, including their carry in. So, this C out from this bit into the next, right? It is also, so it's C out from bit 0, from bit number 0 to bit number 1. Okay, if we number bits from right to left, starting from 0. But then at the same time, this C out is C in for bit number 1. Right, so for bit number 1, this is an incoming carry, and that means that this bit just needs to add this incoming carry along with their, its own bits, A and B. So basically it means that for each bit position, we need to add 3 values. We need to add C in, we need to add our A, and we need to add our B. And then we're going to have the result, and C out, and C out can be 0 as for bit number 2, or it can be 1 as in bit number 1. All right. So, and for bit number 1, when we are summing 1, which is the carry in for this bit, 0 and 0, we get 1, and there's no carry into the next bit. So, or we can say the carry is 0, the carry out into bit number 2. So the carry in for that bit number 2 is incoming carry is 0, 0, and 1. So the result is 1, no carry again. And when we do bit number 3, it's 1 and 1, it's 0. And then there is an outgoing carry into the next bit, bit number 4. And then in that bit, we are adding 1, 0, and 0, and the result is 1. And there is no further carry. Okay, so and that's what we really want to implement with our ALU, that kind of binary addition. So we see that O naught, O sub 0 is the carry, and O1 it refers to the notation from the previous slide, is the sum. All right, so and we just went through this interactively on the previous slide, right? So we are adding 3 bits, okay? So 2 bits that are part of the values that we are adding, and then a carry, an incoming carry. All right, so given that, we can come up with a revised truth table for addition, because we are now adding A, B, and carry in at the level of each individual bit position. And then we have 2 output signals, carry out and sum, right? So those are inputs, and those are outputs. All right, so for the outputs, we have two of them, but that just means that you have two functions, okay? So that is not a problem, right? And here is the truth table, of course, for when we have three zeros, the result is 0 and carry out is 0. If we have 0, 0, 1, the result is 1 and there's no carry. So when are we going to have a carry out? Well, we're going to have a carry out when we have two ones or more in their inputs. Okay, so let's look. Carry out because we have two ones here. Carry out because we have two ones here. Carry out because we have two ones here, and carry out because we have even more than two ones here. Okay, and then the sum is pretty straightforward, right? So, like 1 and 1, if we do partial sums, just to check, right? 1 and 1 is 1, 0. And then if we add another 1 to it, is going to be 1 and 1, which means 1 is the result and 1 is the carryout. So to perform the logic design for our new adder, we can derive SOP expressions from the truth table above. We can build then a combinational circuit that implements those SOP expressions, and we can put it in a box and give it a name and say that, hey, this is our adder now. So this is what is known as the full adder. Because it has this carry in signal. Okay, the adder that we designed previously does not have a carry in, and we call it half adder. Okay, so that's the component that we can now reuse. And so this is a 1-bit adder, right? So A and B are just each is a 1 bit. So we need to be able to combine those adders so that we can do 4-bit, 8-bit, 16-bit, 32-bit, 64-bit, however many bits we need for addition. All right, so to build a 32-bit ALU, what do we need to do? Well, we need, a 32-bit ALU is going to be a box, again, a black box, that will have 32 bits of one argument, 32 bits of another argument, okay, and 32 bits of result. And the OP is going to be the control signal or signals to select which operation this ALU performs. Remember, ALU performs multiple operations, and or addition, those are just the ones that we discussed, and it can actually do even more operations. Let's start with 3 different operations, and or and addition. Okay, so 64 inputs because there are 2 times 32 arguments, 32-bit output, and 3 different operations. So how many control signals do we need? So this, if you look at this input here, then you see that it's kind of thicker than the others, right? So this one is just an individual bit. That's why it is a thin line. This one is called a bus because it combines multiple lines, multiple signals. So can you tell me how, for a bus, it's quite common to use the notation, and you will see it like this is a bus, and then you kind of put this line here, and you put the number of wires or signals that are in this bus. Like, if this bus has 15 wires or 15 signals, you just write 15 next to this slanted line. All right, so how many wires, how many signals do we need in the OP bus? How many? Just two, exactly. All right, and we're not gonna, so 2 control signals for the OP will allow us to encode 4 operations, and we're only gonna use 3 for now, okay? But it's okay, so the 4th combination is just not gonna be used at the moment, right? And later on, you will be asked to add not even another operation, but two more operations. So you will have a total of 5 operations. And that's when you will realize that, oh, I need an additional control signal. I need to have now 3 wires in my OP because I need to have 5 operations. Why 2? Because if you have just one OP, it is either 0 or 1. So you can code, let's say this is add, this is OR, but then you don't have any combinations left to encode the third operation, right? Addition. So you need to switch to at least to 2 bits. And there will be, this fourth combination that is not currently used, but it's fine. You can have unused combinations. All right, so that's our 32-bit ALU, like the overview, right? The black box without any details of what it consists of. But now let's look at the actual contents of this black box, right? So this is the contents of that black box. So we have our 64 inputs here, right? So here we have 32 A's and 32 B's. So this is our these are two numbers, or two 32-bit values to be more precise. This is the operation, but remember, operation is 2 bits, right? This is a bus. This is not a single wire. This is a bus that carries 2 signals, or 2 wires, right? And then we know that we need to have a carry in. So here comes the need for an additional input signal. Okay, so we have carry in for each of the ALUs, and so each component is a single bit ALU, and that's how we combine them. You see that the carry out flag from 1 bit is the carry in for their next to the left, for the next more significant bit, and that's why we have to chain them. We have to wire them like that to ensure that if we have a carry, that it is a carry out, it is actually connected to the carry in input of the next more significant bit, to the ALU that implements operations for the next more significant bit. Okay, and operations are the same. Of course, we want all our 1-bit ALUs to implement the same function at any given moment of time. That's why the operation is fed like in parallel to all the ALUs, right? We don't want some bits to implement AND and some bits to implement add, right? We all bits to implement the same function so that our ALU, our 32-bit ALU, works as a whole correctly. All right, so, and this method of connecting the carry signals is called the ripple carry adder, right? So for AND and OR, carry is not used, right? For AND and OR, the result only depends on the values of those inputs. Carry is not used for any bitwise logical operations, AND, OR, and whatever. It is only used for addition or operations related to addition, like subtraction, as we shall see shortly. All right. So why is it called ripple carry adder? Well, it's because we see that if there is a carry here, and let's say it's 1, then if we didn't have that carry and we had 1 and 1 here, 1 and 0 here, okay, we would not have a carry out from this second bit, right? 1 and 0 is 1. There's no carry from that bit. But if we didn't have a carry in, but if we have a carry in and that carry in serves this 1, then we have to consider it, and we have 1, 1, and 0, and the result is 0, but then there is also a carry. Okay? And the problem that it is raising is that, well, how long will it take this 32-bit adder to compute the result? Okay? It turns out that the result can only be considered computed when all bits of the result, all of those folks, are are computed. So that means that the slowest of the bits of the result will be the bottleneck. Which one will be the slowest? Well, we can see, imagine the following scenario. We supply the values for, to the inputs to all our A's and B's at the same time. So it's 1 and 1 and 0 and 1. And 1 and 1. Oops. 1 and whatever. Let's say it's even if it's 0, 0. Okay. So is our ALU 31 the ALU that performs the most significant bit? Can it produce the result? Well, if let's say, well, it's 0 and 0, so you might think, oh, it's 0 and we are done. Okay. Well, not so, because we have this carry in. So before carry in is supplied to our ALU 31, this result is iffy, because it may actually not be the real result, right? If carry in comes in to ALU 31 and that carry in is 1, the result 31 is going to be actually 1. So that result cannot be computed until we know the carry in into ALU 31. All right, who determines their carry in into ALU 31? It's going to be their carry out from ALU 30. Who determines the carry out for ALU 30? Well, it is a function of A30, B30, and carry in 30. So it will be determined by the carry out from ALU 29. So you see there's a chain, and it kind of starts with the least significant thing, right? 1 and 1, the result is 0, and then this carry out is 1, and now we are certain that this is the right result. So now, once this carry out from bit 0 into bit 1 is known, we can be certain that this ALU 1 computes the correct result. Okay, what would be the correct result? Well, it's going to be 0 and 1 as the carry out. Okay, and then ALU 2, the result would be 1, and carry out would be 1. So you see how this carry signal kind of travels through all the ALUs, through all our single bit ALUs, and the result is only guaranteed when the carry in is computed correctly for any ALU. And of course, ALU 31 is going to get its carry in the last, because it's the last in this chain. So you see how this carry signal ripples, right? And that is not the most efficient way to actually do it. And we will talk about it a little later. But for now, you can see that, this propagation of the carry signal has to go through all the bits. And then if it turns out that, yeah, there is a carry out from ALU 30, which is a carry in into ALU 31, then yeah, it's no longer 0 result, it's actually 1. Okay, but for that, this carry has to travel through all the previous ALUs. Okay, so that means that carry out must propagate through all those, through all the less significant adders. Why does ALU 0 have a carry in signal? Well, for one, we have a standard component. All right, this is the component that we're using. It has a carry in, and unless we have a good reason to design one of the ALUs for a specific bit position differently, we would prefer to just use, ready-made components, right? So what do we need to supply to the carry in of the least significant bit? Yeah, interchangeability. I like how you put it. That's a strong point, right? You don't want to have custom components unless you have a good reason to, right? So for this to work for addition, what do we have to supply? It's an input, right? So we have to put something, to connect something to that input. What do we connect to that input? the carry in of their least significant bit, right? What do we need to supply here? So someone says, I assume ALU31 would also have a carry out output then. Yes, thank you. It's not drawn, but let's fix this. It should. But with the output, it's never a problem because, like, even if we don't need that output, yeah, we can, let it be. Let's let this output stay there. We don't even have to connect it to anything, and it will be the arithmetic overflow exactly, right? But if we're not concerned, if we don't want to know about that, we can just ignore it and just not connect it to anything. With the input signal, you cannot leave it hanging. All input signals have to be connected to something. Okay, and of course, in real life, it's more complicated than that because you have, tri-state, and you have, pull up and pull down. The idea of pull up and pull down. So, but in our simple logical view of this circuit, we just need to make sure that all inputs are connected to some logic signals. Okay, we cannot just have this carry in floating around because we would not know whether it gets value of 0 or 1. And of course, this carry in does affect the whole computation. So what do we need to supply for carry in? How do we connect this input? Any thoughts? Zero, exactly, right? So it's just a constant 0. We can write it like that, okay? But you have to connect it to something, okay? And we actually, we shall see very, very soon that there are cases when you actually want to connect it to not 0, right? And that would be a trick that would help us a lot. But for addition, we definitely want this carry in at 0, okay? All right, so, and here is their second pop quiz for today. And by the way, you folks are doing great with those sub-mini polls. So I think one person already earned 3 extra late days. So they are now at 6 late days overall. Okay, instead of 3 that we started with, and a lot of people are at 5 and 4. So I think you're doing great. All right, so that was addition. Now, what do we do if we want to approach subtraction? Well, let's first think about the idea. Well, we can do addition very easily if we, instead of doing a minus b, we just do a plus minus b, a plus negative b. So if we could negate b, then we would just use the same adder to implement our subtraction as we do with our negation, okay? And as we do with our addition. And that is a very attractive idea, but we need to decide, like, can we negate b? How do we do that? Okay, so here's the idea. And we are assuming, of course, 2's complement notation, right? Because as we discussed, it seems like the most convenient method. So what if we need to get a negative of the number? We just have to invert all bits and then add 1 bit to their least significant bit. So here's the trick. We invert all bits of b, and then we add 1 by just setting this initial carry in to 1. So here, instead of using 0 for carry in, we can use 1, right? Because we need to add that 1, but only in case when we are subtracting. So that gives us, that's a slight complication, but basically that means that whenever the operation is add, we have to make sure that carry in is at 0. Whenever the operation is subtract, we need to have the carry in as 1. What about and or? What should be the value of the carry in for and or operations? What do you think? There are no, they don't use carry in for them, but we have to set the input to a certain state. Okay. And it is either 1 or 0 for those operations. It doesn't matter. So you can accept pretty much anything. And here we get to the concept. Let me draw it here of don't care, and it's pretty important. And it will don't care state. So don't care really means 0 or 1, and we would use either a question mark or an X to indicate this this don't care. Okay, so let's say that we have our OP 0 or OP 1 and 0 1 1 0 1 1. So and I'm just assigning arbitrarily for now their functions and or add and sub. Okay, and this is what we want to feed into carry in. So it has to be a separate circuit which produces this carry in signal. So it would be like a black box that we're trying to build. It takes OP and it produces, this carry in. It's not carry in for this circuit. It's an output, but we will connect this to the carry in of our 1-bit ALU. Right? So that would be carry in for this 1-bit ALU. Okay, so we need to first build this truth table. So for addition, we know that carry in should be 0. For subtraction, we just discussed, carry in should be 1. And for and or, we don't care, which means we can treat it as 0 or 1, whatever we find more convenient. Okay, so for example, can you come up with a single gate that would allow us to implement this black box that we're trying to build? Just treating those axes, those don't cares, to your advantage. Exactly, you can do an AND. Okay, so this would be OP0 or OP1, and this would be exactly this carry in that we are trying to do, right? And it's just a simple AND because it guarantees that, the important thing is that for this combination of inputs, the output is 1. For this, it is 0. And for these two, we don't care. It can be 1 or 0. And in this case, it's 0. So it works. Okay. Because if it gives you the don't cares really give you a lot more freedom in minimization of Boolean functions, right? Because then you can treat them as either 0 or 1 to your advantage. So if you were to build their K-map, all right, and you would have, so let's build, there's only 1 0. 0 1 0 1, okay? And you have 1 here, okay? So you can, and you have, and this is, let's say, OP0, and this is OP1. Okay, so we need to make sure that OP1 1 0, this one is 0. Okay, but this one you can treat as zeros or ones. So, for example, you could, in this case, it's probably not going to make sense, but you could have decided to cover them and treat them as ones like that, right? It's not going to be the best way, right? Because it wouldn't be minimal. So there you can do it with one gate if you treat those x's as zeros, because then you only have to cover this one, and that's it. Okay. Or someone says, exactly, you can just do OP0. And why? Can you show me the K map? How you would do that? So you would treat this X as 1 and then cover this region in your K map. And for this region, you see that OP1 changes, so it doesn't matter. OP0 is 1. So the whole function is OP0. Okay, so here you treated this X as 1, this X as 0 to your advantage. So you were able to, actually provide an even more minimal, right? So this is the true minimal solution. Okay, very good, very good. You are staying on top of things. Okay, so that was my um, a note about the don't care. Please use them to your advantage. In many cases, there are signals that are not applicable for particular modes of operation, and then that means that they have a don't care state that you can just that you can take to your advantage, whatever you think you need. All right. So here's our revised 1-bit ALU. So we have this, and this is not the only possible design. And I will actually ask you to do a slightly different design in a little while. So, but this design has the same operation, right? Which only encodes three things: add, and or. So there is no explicit operation code for subtraction. But if you want to do subtraction, you have this additional control signal that determines whether B is inverted or not. What is this component? It's not labeled here and here. These two components that look like, ellipses kind of. What are those components? Can someone guess? Well, this is a not. This is an invert. I'm talking about this component here and this component here. Exactly, they are multiplexers. So this is a 2 multiplexer, and in your circuits, please label them clearly so that we don't have to guess. But this is a multiplexer. B invert is the control signal, is the selector that decides whether output is connected to B or not B. Okay, this is, in a sense, like, programmable, controllable inversion. Okay, and this is the adder, right? So the plus sign kind of hints that this is an adder, and so carry in will be fed from our circuit that we designed before, and of course, if their states of if their operations are encoded like that, then we already discussed it can be just the OP0 signal, but it depends on how you encode. All right, so I don't know whether here encoding is the same as we assumed or it's different, but even if it's different, you can easily make this black box. All right, so at most it's going to be one gate. All right, so and so this B invert controls whether B is inverted or not when B is fed to the adder. And so if you were to do B invert for the operations, right, for the OP, so let's assume the same encoding that we used for OP1 and 0, OP1, OP0, 0, 0. And now we have this B invert, which is an input, okay? And we need to determine, like, what to supply to that input. And 0, 1, 1, 0, 1, 1. And we had and or add. And we had and or and add, right? And this is not used, right? The fourth combination is not used because our operations are here, okay? So when we supply B invert, that would be like the subtraction, okay? So that means that for and we need B invert at 0, right? Because note that the same B is fed to our gates that we form and or. So it's not don't care in this case, right? For and or, we want B invert to be 0. And for add, it depends whether we are performing addition or subtraction, right? So it would be exactly 0 or 1. And if it's 0, it would mean add. And if it's 1, it would mean subtract. Okay. And then, of course, this carry in will be, if we draw this circuit, right? This circuit is going to have inputs as OP1, OP0, and B invert. Okay, because B invert will also determine whether this carry in is 0 or 1. And you can see that here it's going to be very easy. Carry in is exactly B invert. When we want to subtract, all right, B invert is 1, and we want carry in to be 1. So really, this is just B invert here. Okay? So basically, we can just connect it like that. All right, whenever we do B invert, carry in will be 1, and we only do B invert when we want to do subtraction. And so this is a 4 multiplexer here, right? We are only using 3 inputs, right? Because we don't have a separate sub operation. We do sub slightly differently, as you can see. But that's also a multiplexer that is controlled by the operation bits, and they determine, which result is connected to, which function is connected to the result output. Okay, so basically it's like, you can think of it as our ALU always performs all operations, but we only select one that we want to show to the outside world. Okay, but it's always doing all the work no matter what. Okay, and so if we want to route the output of the AND gate, then we will see that we have to make sure that input 0 is routed to the result, which means that our operation for AND is 0, 0. So exactly like that. If OR, it's input 1, so our operation bits should be 0, 1, 0 for OP1, 1 for OP0, and this is 2 for addition / subtraction. Okay, because the subtraction is determined by whether B invert is 1 or not by an additional fourth combination, by the fourth combination of the operation. Okay, is that making sense? Are we good with this revised 1-bit ALU? Are A and B here the same as OP0 and 1? No. Those are A's and B. So this is an A, this is a B. Each is 1 bit. And this is actually a bus that contains 2 signals, OP1, OP0. So operation is also an input, but operation we call control signal, whereas A and B we call data. Right? Data is obviously what we operate on. So whatever we are adding or ending or ORing, this is our data. Result is also data, but the result is output. And operation and B invert are control signals, right? They just determine which operation, how this circuit functions, right? We are not doing anything with OP0, OP1. We're not adding them, right? They're not data itself. They're just control signals that kind of modify the behavior of the circuit. Right? Making sense? All right, and so with this, let me see. Okay, yeah. Before we get any further, here is the exercise problem for you. Okay. No, not making sense. Oh, making sense. Why is it not? Don't care again. For B invert? Well, because if you do B invert don't care, and let's say for an AND operation, you decide to take B invert as 1, then it will invert B and it will route it to an AND gate. So instead of doing A and B, your ALU will be doing A and not B. So that would be a different function. So you don't want to invert B unless you are doing subtraction. Okay, and subtraction would require that we use the adder, right? So the subtraction is only when we have this state of their control signals for operation. Okay, this is the only mode, right? When OP is 1 and OP is 0, when you can actually do subtraction. Okay, if you're not doing this addition slash subtraction, you want your B invert to be at 0. Okay, still makes no sense to you. All right. Well, if we have many people for whom it's not making sense, I can go over it again. If it's just a few people, maybe we can push it to their office hours. B invert is confusing. Yeah, so B invert, it is a control signal that determines whether your adder gets an inverted B or not. Okay, because if it's get and not inverted B, then your adder will add A and B. If it gets an inverted B, then it is part of the subtraction. Yeah, B invert literally says what it does. Okay, it inverts. It's the control signal that when it is at 1, it means B will be inverted. If it's at 0, it means B will not be inverted. So it's like a programmable inverter. Okay, so what's the point of having a NOT gate on one instance of B? Well, B is just a single bit, right? And we only have one instance of B because it's a 1-bit ALU. So this inverter, we need it because this B invert flag needs to be deciding what to route to the output, and it needs to route either B straight, B straight, B straight, or B inverted. So this multiplexer needs to have a B inverted or not be on one of its inputs. Otherwise, how would it be able to produce B inverted at the output? Okay, that's why we need to invert B so that this multiplexer has a choice whether to route B or not B to the output. How does it know which to pick? We tell it with exactly the B invert. So B invert is the flag that we set. It's an input. So when you use your ALU, right, you set B invert to 1 if you want to perform subtraction. And you set it to 0 if you want to perform addition. Okay, and yeah, B invert is the control signal, right? So the convention on this in those slides from the textbook will be this yellow orange color is used for control signals. Okay, yeah, thank you, folks. You are helping me a lot, by helping other people to understand it. The concept. It's a difficult one. Okay, so I was getting to the exercise that I wanted to do. So implement the same 1-bit ALU just instead of this separate B invert, right? Do not do this B invert thing, but make their operation include their sub as the fourth combination. So this is and, this is or, this is add, and this is sub. Okay, is that clear? What I want you to do? So you will need to change this circuit slightly so that their sub is encoded not as operation add plus B invert control signal, right? As two separate control signals, but is encoded as an operation under the operation bus, under the operation control signals, two of them. Okay, is that making sense? So the circuit that I want you to build would have the result, would have two OP signals, would have A and B, and carry in, and it would have C out, like that. Yes, totally. You can use all the components that we discussed, definitely. Okay. I just want you to get rid of the B invert as a separate signal, and instead move their subtraction as an operation under their OP control signals. Are you allowed to add components? Yeah, you may use and or gates. Well, this is exactly what their ALU would look from the outside. If you're talking about their original form with B invert, so this box here is what their 1-bit ALU would look like from the outside. So I think we have so something like that, except for with a B invert, right? So you can see that each box is here with the B invert is actually what we originally talked about here, right? Before I crossed out the B invert. All right, so our ALU is now capable of performing 4 operations: A, addition, subtraction, or and AND. And we still need, of course, to get the right values to their ALU, to their data inputs, and set the control inputs correctly. So now we are moving forward. Is B invert the same as status? We don't have any status here. There's no signal called status here. I'm not sure what you're referring to. All right, so we are now expanding the list of operations supported by our ALU. It used to be 4. Now we also want the SLT instruction, or the SLT operation. Okay, so so SLT, right? If you recall, set less than. All right, so this is the operation that is 1 or 0, right? 1 is if it's less than, and 0 if it's not less than. So behind this less than, of course, is subtraction, right? Because to find if something is less than something else, you subtract and you look at their sign. If the sign is negative, then their first thing was less than the second thing. Okay, so it shouldn't be that hard to implement SLT for us, but we have to look at this in the perspective. So obviously at the level of a single bit, it doesn't matter, right? Because it's trivial. It's not going to be very interesting. So we really need to look at the case when we combine our single bit adders into something that has more bits, like 4 bits or 32 bits. All right, so let's say this is result 0, result 1, result 2, result 3. Let's do for 4 bits for now, in a very, general outline. Okay, so what does it mean that I want to set the value of the result to 1 when I treat this as my number? It means that R0 should be 1 and all other bits should be zeros. This is number 1, right? This is this value 1. And 0 would mean it's just all zeros. Okay? So what does it mean to be less than? And we just mentioned that it's going to be the sign bit. Where do we have the sign bit? The sign bit is actually the most significant bit, right? So this is the sign bit, right? Right here. Okay? Well, this R3. So when R3 is, and it's R3 of the result. Okay, so when there is this result that is 1, we know, oh, okay, it means it's a negative and we need to set. So we kind of have to kind of circle it back to from the most significant bit to the least significant bit, because when the most significant bit is 1 after we performed subtraction, it means that we need to set to use that 1 as the result for the least significant bit, because we want to set the value, right? If we want to set the value of a 32-bit register, right, so it would be, right, so it's still going to be 1 in the least significant bit. Okay, so that's, let's see how we do that, right? So to support SLT instruction, we need to compare two numbers, which means we have to subtract. And when we subtract, if the result is negative, then A less than B is true, and we need to set, right? So that means if A and B is true, our output, our result should be this 1, right? Because it's set when less than is true. And if false, we set the result to all zeros, just like we discussed. Right? So to compute less than, we subtract B from A, which means we set B invert to 1. We set carry in to 1 to perform subtraction. And the result for all our 1-bit ALUs, except for the least significant, should always be 0. Like here, right? So all those ALUs, except for their least significant, right? This is the LSB, right? The rightmost. So the results for those ALUs are predetermined. They are 0 in this mode, in the SLT mode, right? And this, the value, the output of the LSB is determined by the sign, which is the most significant bit, right? So the result for the least significant 1 bit should be the result bit from the most significant 1 bit. Okay? And I know it takes some time to wrap your head around this, right? But let's let's try doing this. It's important stuff. So the least significant is the rightmost, the most significant is the leftmost, and this is our 1-bit ALU, okay, with SLT. So what has changed is we added this, right? So now our operation is still 4 modes, so 2 bits, OP1, OP0, and the 3 modes are as before, but the 4th mode is this SLT. Okay, so we had to modify because now we have to support this additional operation SLT. Okay, so this is our revised 1-bit ALU. So it doesn't look like terribly that much work, and now their ALUs would be different depending on their bit position. So the most significant bit ALU would be different because it would need to produce, here it actually shows the overflow flag that is coming from the overflow detection unit. But more importantly, here is this set flag. Okay, this set flag is just the value from the adder, right? See how it is routed? So exactly, because when this bit is 1, it means that it's the most significant bit ALU. So if we are talking about the ALU with 32 uh, bits, right, it's going to be ALU 31, right? We use this most significant bit, which is the sign, as a set signal, and we will route it towards ALU 0, okay, because it will determine the output. All right, so that's how the MSB ALU is going to be different from all other ALUs. And here is our final design. So see how the sign bit, right, which is the set signal from the MSB, right? So this is the MSB ALU, most significant bit ALU, is routed back to the less signal of the least significant bit ALU. Right? And all ALUs are the same except for this one, right? So we have 31 identical 1-bit ALUs, and only MSB is going to be different because you see that it has this set signal that we need because it's actually the sign. And then for let's verify that it's going to work correctly. So if for all other ALUs, this less signal is 0, and for the LSB 1-bit ALU, this less signal is the sign bit, 0 or 1. And that's why we see that in our, when OP1, OP0 is 1 and 1, so we have SLT, we see that this less signal will be routed to the result. And for ALU 0, it's going to be from set signal, from set output ALU 31. For ALUs 1 to 31, it's just going to be 0. Okay, so this less is going to be 0 because then this 0 will be just directly routed to the result in mode 3 when both OP0 and OP1 are 1s, which is SLT. Okay, so this is exactly what we see, like all others, and including the most significant bit less signals, they are zeros. Okay, and yeah, the last thing that we need to do is put it in a box, give it a name, right? So for the ALU operation, so this whole thing that we designed here, right? We can just say, well, this is this is 32 bits, this is 32 bits, this is 32 bits, right? And then we can, we can just use it. ALU operation is 4. Oops, not 4, of course. It is 2. Okay, but if in here we have B invert as well and carry in. Okay, so B invert is the control signal. B invert, and carry in is the data. Okay, so that would be our ALU. Okay, so, and yes, if you do the exercise that I asked you to do, then you can come up with an ALU that doesn't have this B invert, but if you support SLT, you would have to increase the number of wires in the OP to 3, right? Because you would now have OP2, OP1, OP0, and it doesn't matter how you encode them, but you would have AND, or, add, sub, and SLT. So you would have 5 operations, so you would need more than 2 bits for that. All right, and we have yeah, we are behind. I spent a lot of time on ALU, but it's a very complicated topic, so I don't regret. So let's probably, yeah, we have memory and IEEE 754. So yes, it's good that we moved the deadline for the homework because then we don't have to rush through this topic. So we will cover it next time, which would be what, Tuesday, and then you still, yeah, and it's a fairly simple topic. So if you ask me, this whole ALU thing is a lot more complicated and a lot more important as far as the rest of our material in this course is concerned than floating point. Floating point is just a standard F format. Yeah, you need to know how the numbers are represented, but usually this material goes much easier than their whole ALU stuff. Okay. All right. We have what, 4 minutes left. Let's then not start the new topic, and so let's save floating point for the next for the next lecture. And what do we want to do? Why don't we look at their my weekend plans? Well, work. It's not exciting. Let's not go that route. It's nothing exciting. Why don't we look at some of their? But thank you for asking. Let's look at some of their circuits that I prepared for you, and I can comment on those circuits, and I can just show them to you. And so I uploaded them all on Submidi under course materials, and they are all from Open Circuits. So. And yeah, let's get rid of this, and I just need to refresh. Right? Unfortunately, well, Open Circuits doesn't save your circuit. If you just refresh the browser page, your circuit is gone. And that I can use to just clean stuff up. All right, and so here are. Okay, so here's half adder. Let's look at it. Okay, and this is a half adder. Why? Because it doesn't have a carry in, carry out. Well, it kind of have carry out. It doesn't have a carry in, so it's a half adder, right? And so let's just look at how it works. It's just directly so now this is 1, this is 1, and of course if both inputs are 1, we have carry out, right? So this is half adder, just directly from the truth table. Really, nothing fancy. And we have a half adder with an XOR. You see how much simpler it is, right? So this component is an XOR, and of course it works exactly the same way because it is the same component, right? It should have the same, it implements the same function. And then a full adder, we're going to have a full adder if it has a carry in. Okay, so those are components, all right, and you can view what this components consists of, right? So this is their design, and I think I showed you before. You can make ICs, you can make components in open circuits, and then those components you can reuse, right? So 3 inputs, so it's a full adder, C in, A, and B. Okay, and if we have C in, you see that we have both carry out and sum. This is sum, this is carry out. It might be hard to see, but we can zoom in, right? So you can see the whole thing. So this is their full adder, and this is how we can make a 4-bit adder using 1-bit adders. Okay, and now we can do like I don't know. It's going to be 7, and then what do you want to add? I know. That would be 3. 7 and 3 is 10. 10 is A. All right. So we can see an A here. So we can verify that everything works. All right. And there's a number of other circuits, so please take a look at them. Don't worry about their SR latch. We didn't talk about it, but all the other circuits you should be familiar with, so please take a look at them. All right, so I think it's 1:50, so our time is up. Thank you very much, folks, for attending this lecture, and hopefully you learned something new, and enjoy your weekend, okay?